All right, let's get started. So today we start now chapter 5. Chapter 5 and 6 are dedicated to the idea of an integrals. And we've already started a little bit with integrals and antiderivatives, almost synonymous. And so I told you there's 4 big ideas in calculus. The idea of a limit, the idea of continuity, the idea of a derivative, and then finally the idea of the integral. So this is the last major idea that we're going to be covering. Now, just quick intuition for what an integral is. When I say a definite integral, you've been solving indefinite integrals thus far. Okay. Our intuition for an integral from a to b of f of x with respect to x. Our intuition as we develop what this means, the intuition that we're going to follow, is going to be the idea of area under a curve between 2 points, A and B. The same way that f prime of x naught means the slope of a function at a point x naught, right? That's what the derivative gave us. Gives the slope of a point at x naught. The integral from a to b of a function is going to give us the area under the curve of that function between the points a and b. That's intuitively what it gives us.
Just going to the x-axis?
Yeah, just going to the x-axis. So there's the x-axis, here's the y. Correct. That's the intuition we'll be using to develop what we think integral should be. And we'll follow something very analogous to what I did in calculus, or what I did with derivatives. Remember what I said with derivatives? We start out with some curve. And I said we can start out with the secant line. So I want to approximate the curve at x naught. So we're going to start out with this terrible approximation, go to this point x, right? And we'll look at the slope of that secant line. And then we'll make the x get closer and closer to x naught, making our terrible approximation get better and better and better. Yeah. We'll do something analogous with areas for calculating an integral. We'll start out with, we'll approximate the area with just a bunch of big rectangles. So I'll approximate by calculating the area of this rectangle and this rectangle. And then we'll add more and more and more rectangles. What happens if I were to divide it and use this rectangle, this rectangle, this rectangle, and this rectangle? As I use more and more rectangles, we get closer and closer. So that's intuitively where we're going with integrals. Okay. Now I'm going to cover this a little bit different order than what the book does. First I'm going to cover sigma notation. I really wish we had another eraser. Where's that little one? So first I'm going to cover sigma notation, which for Peter is probably not much, but I don't know if you've ever seen this before, Jeremy. So sigma notation, that's a lot of section 5.2. Then we'll go back and I'll just develop the notion of an integral, ignoring the book altogether, and then we'll come back and follow the book's way. Because the way the book does it is 5.1 and 5.2, these are kind of setting you up for what an integral is. It does a very slow development, and then 5.3 is finally where you get our definition of an integral. Oh, right. And we won't be covering this until next week.
That's right.
Okay? So a lot of what I'm going to cover today in class, you won't have homework on for a little bit. Now 5.3, if there's one section of the book I could get you to read for the next 2 chapters, it is this section. If you can wrap your head completely around this section, you're set for chapter 5 and 6.
Okay.
The same way that understanding a limit early on kind of set you up for understanding all of chapter 2. Understanding this early on is going to set you up to understand all of chapter 5 and chapter 6. So we won't be getting to that today, but we'll naturally develop the notion of an integral. So first we'll start with sigma notation. So sigma notation looks something like this. We are going to sum up from k equals 1 to n the terms a sub k. This is it written in its most general form, and then we'll get to a lot of specific examples. What does this mean? This means we are looking at a sub 1 plus a sub 2 plus dot 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 plus a sub n minus 1 plus a sub n.
Isn't it plus or times?
Plus. Sigma notation is plus. Times notation is times.
That's right.
Product notation. So that is what it means in its most generic form. So let's look at one really quick concrete example of something this might look like. So let's say we're looking at the sum from k equals 1 to 11, and what do they want to do? K squared. K squared. What does this look like? So how we do it is we plug in 1 for k, then we plug in 2 for k, then we plug in 3 for k, then 4, then 5, and 6, and 7, all the way up to 11. So this is shorthand for this is where you start, this is where you end, this is what you plug into. So when I plug in 1 for k to this expression, what do I get? 1 squared. Then I plus, what do I get when I plug in 2 for k? 2 squared. Plus 3 squared, plus 4 squared, plus, and I keep going, and I stop once I reach the top number, 11 squared.
Okay.
So you have some expression in terms of whatever the variable is that you have written down here. Down here I have k, so I'm going to say, in this expression, I'm going to replace k with 1, and then I'm going to replace it with 2, 3, 4, and keep going until I reach this top number, 11. That's what this is generically saying. You have some expression dependent on k. You start at k equal to 1, and then 2, all the way up to k equal to n. Here's where you stop.
Do you always add?
Yes, it's summation notation, meaning it's a shorthand way of writing a massive sum.
Okay.
Does that make sense?
Mm-hmm.
So let's just write some really simple ones really quick. So what if I say the sum from k equals 2 to 5 of k? What's that equal to?
2 plus 3 plus 4 plus 5.
Perfect. That's exactly right. Let's try another one. Let's look at the sum from k equals 0 to 5 of k squared over k minus 1. What's that equal to?
0 plus.
Oh, doesn't work. I gave something undefined. So I didn't write this down the same way he did. He did plus 1. Still starts at 0.
And a half.
Plus 1, yeah. Perfect.
4 thirds.
4 thirds.
9 fourths. 16 fifths. 25 sixths.
Perfect. So that's all sigma notation is. It's shorthand for a way of writing a really big sum. So let's go the other way. Let's express this in sigma notation. So let's say I'm looking at 1 plus 3 plus 5 plus 7 plus, I'm not sure where he stops. I think he stops at 9. 9. So how can we represent this in sigma notation? So we're trying to represent this sum.
Okay.
So we can do the sum from, let's see how many terms we have. 1, 2, 3, 4, 5. I have 5 terms. So wherever I put my start and end point, we need to have 5 terms. What should we start our k with?
K equal to 1.
You want to start with k equal to 1? So if I start with k equal to 1 down here, then where do I need to end?
K equal 5.
5. So now, what would give me 1 when I plug in 1?
Just K.
Just k. But then what would give me 3 when I plug in 2?
Plus 1.
But that doesn't work.
That doesn't work. So we got to try and come up with a pattern for these things.
Okay.
So we need some expression in terms of k that gives us these numbers.
2k minus
Now I think it's going to be easier for us if we start k at 0 and go to 4. Or, no, we can do exactly what he said. Okay, that works actually. 0, 5, oops, 1, 5. And what did you say?
2k minus 1.
2k minus 1.
Oh, yeah.
Notice that they're growing by 2. So that tells you that you're going to need a 2k in there somewhere.
Yeah.
Because for every 1k you add, you need to increment by 2.
And they're also odd.
So you needed a 2k in there, and then, yeah, they're also odd, which is why I was going to do 0 to 4 plus 1, because then we're using the definition of odd, but this
Yeah.
works just as well. There's nothing wrong with that. That's a perfect answer. Okay. And notice that there's infinite answers to this question, by the way.
There is?
Yeah, let me give another one. I'm going to do k equal to, we're going to start at negative 10, and then I'm going to go to minus 5,
You just change the constant.
because you just changed the constant.
I see. So you change the plus 1.
So when I plug in negative 10, we get negative 20, so I need this plus 21.
Yeah.
So there's no one right answer to these things. So don't think you're looking for the solution. You're looking for a solution, something that does work.
Okay.
Make sense?
Mm-hmm.
Okay. Let's look at one example that motivates an idea. So we're going to look at the sum from k equals 1 to 3 of k squared plus k. Now you need to use parentheses at the end of an expression in case you continue on. Right? So if I would have said the sum of this plus 2, then this is saying do this sum, and then add 2 when it's all said and done.
Okay.
So with the 2k minus 1, we would put parentheses around the 2k?
The 2k minus 1, no, around the whole thing. Here's what's giving me my terms, but I could have this as part of a bigger equation.
I see.
Okay. So, let's see what this is equal to. What's this equal to?
2.
Well, we're going to write it out longhand. So it's equal to 1 squared plus 1, plus 2 squared plus 2, plus 3 squared plus 3. Right?
Mm-hmm.
Okay. Now I'm going to rewrite all my squared terms first, and then my linear terms second. So this is the same as 1 squared plus 2 squared plus 3 squared, plus 1 plus 2 plus 3, right?
Mm-hmm.
And you can think about it like this if you want. It doesn't change anything. Put parentheses around that, put parentheses around that.
Okay.
Agreed? I haven't changed the expression.
Mm-hmm.
And so then I can say this is equal to the sum from k equals 1 to 3 of k squared, plus the sum from k equal 1 to 3 of just k. So notice, if I have the sum of an expression, if I'm summing, this is bad because I'm going to use the word sum twice. Let me think about another way to say this. A sigma of a sum is the sum of the sigmas. Oh, why do we call it sigma notation? That's the name of that Greek letter right there. Sigma.
Sigma.
Yeah, sigma. Sigma. So it's called sigma notation or summation notation. The reason sigma gets in there is because that's just the name of the Greek letter. That's just a Greek letter. Sigma.
Okay.
Okay, so the sigma of a sum is the sum of the sigmas. Which makes sense.
Yeah.
Because this is just a sum of a bunch of terms. You can reorder sums however you want. They're going from here to here. What property of sums did I use? They're commutative, meaning you can do them in any order you want. And they're associative, so I can associate those three together and those three together.
Oh, I see what you're saying.
Okay. So, in general, we're not going to prove any of these because we're just trying to familiarize you with the notation. Obviously, we proved all these things in discrete math. But in general, what do we have? We have the sum from k equal 1 to n of a sub k plus b sub k is equal to the sum from k equal 1 to n of a sub k plus the sum from k equal 1 to n of b sub k. Which hopefully now makes intuitive sense.
Yeah.
Okay? Similarly, if this would have been a minus, we could replace this with a minus and it's the same thing. Let's see that in our example real quick. If I would have had a minus here, I put a minus here, which puts a minus here, which puts a minus here, and then I could replace that with just a minus there. And it puts a minus there. See that?
How about divide and multiply?
No. Multiplying sums gets really, really hairy.
Okay.
Think about if I do this sum, or this product, k equals 1 to 3 of a sub k times the sum of k equals 1 to 3 of b sub k. What is that saying? That's saying we're doing this. a1 plus a2 plus a3 times b1 plus b2 plus b3.
I see.
And that, you'll notice already with 3, that's blowing up into a bunch of terms. Obviously for bigger ends, it's going to blow up even more.
What does the sub k mean? Is it just
The k is what we replace with the numbers. So I wrote a sub 1, a sub 2, a sub 3, because it was a sub k. I took the k in this expression and replaced it with a 1, and wrote it there.
okay?
I took the k in this expression and replaced it with the 2, wrote it there. It's the exact same thing we did here. I took the k in this expression, replaced it with the 1. That's what we did. So this always signifies the variable you're going to replace, what you're going to start replacing it with, and what you're going to end replacing it with, incrementing by 1 as you go.
Okay.
Okay.
What if it was at 1/2?
We don't have that.
Okay.
Oh, so you can't start at like 1/2 or a fraction? Has to be a
No,
whole number.
you'll never see that.
So what? It's just the integers?
Yes.
Okay.
Okay. Let's look at 2 more things. So we saw the plus, we saw that. Let's think about what happens with a constant. What would happen with a constant if I did the sum from k equals 1 to n of some constant c times a sub k?
Then it's just c times a1, c times a2,
C times a3,
so on and so
etc.
forth. Yeah.
And then I can factor out all those c's from the sum.
Mm-hmm.
Oh, so okay.
So it's the same thing as c times the sum. You see that?
Yeah, but it has to be constant, right?
Yes, it has to be a constant. This can in no way depend upon k, otherwise this does not work.
And we saw why.
Has to be a constant, because you have to factor out the same term from everything. Okay, does that one make sense?
Mm-hmm.
All right, and then the last one, I want you to tell me what this equals. The sum from k equals 1 to n of c. What does that equal?
C n times.
N times c. Because you're going to c plus c plus c plus c plus c, n times.
Oh.
Make sense?
C doesn't. Oh, I see.
Okay. So with those in mind, let's do a couple more concrete examples. And then I think you're pretty much getting this notation down. So let's look at this one real quick, because this might throw you for a loop. Let's look at the sum from k equals 1 to n of 1 over n. Okay. What's the first term in the sequence?
1.
1.
Over 1.
That's what I was afraid was going to get you.
Oh.
Replace all your k's with 1. And what do you get?
Well, you don't have case.
So what do you get?
Nothing.
1 over n.
You get 1 over n plus 1 over n plus dot 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 plus 1 over n. This up here is a constant. This is your variable.
So you do 1 over n plus 1 over n times, right?
Yes.
So it's
So
the
what's it
same.
equal to?
N times 1 over n.
Which is
1.
N no.
1.
1. Oh, you're right.
There you go. So just 1. So make sure you pay close attention, because there's something instinctual about treating n's as variables. Right? And you naturally, without even thinking about it, you want to replace the n with 1, the n with 2, the n with 3. Don't fall for that trap. N is a constant. K is your only variable. Whatever the letter is that they have written here is a variable. Okay? So I think that's a common gotcha with these.
What do you do if there's multiple variables and a k?
Treat every letter as a constant, except for the thing listed down here. That's your only variable.
Okay.
Because the only way whatever you have written here changes is if k changes. And so it has to have a k in the expression. If there's no k in the expression, it's not changing. So any other letters have to be constants. Does that make sense?
Mm-hmm.
What if it's just like the same thing except 1 over 2 n times?
So if we had 1
Yeah, 1 over 2.
1/2, what does that equal?
Is it just n over 2?
Yeah.
Okay.
Yeah, you just have 1/2 plus 1/2 plus 1/2 n times. So it's just n over 2. That's exactly right.
Okay.
Good? Okay. Now, again, since we can't use proof by induction in this class, but we need to figure out what some of these what some of these sums equal, we'll have to do a roundabout proof. We're going to prove one, but then I'll just write down some equations that, unfortunately, you're probably just going to have to put on your formula sheet or memorize. But let me give you the first one. So the first one that we're often interested in, a sum that we're often interested in, is the sum from k equals 1 to n of k. And we want a generic expression for what this equals. Now notice what this is asking. This is saying, what is the sum of all the numbers starting at 1, ending at n? Right?
Mm-hmm.
If n, for example, were equal to 10, what would this be?
10.
This would be 1 plus 2 plus 3 plus 4 plus ... all the way up to 10. In our case, we're going all the way up to n. So what does this sum equal? That's what we're trying to evaluate.
Okay.
You with me?
Okay.
So I'm trying to figure out what's 1 plus 2 plus 3 plus 4 plus n equal to. I'm coming up with a formula. So for example, if I ask you, add up all the numbers between 1 and 1,000. Right now, how would you do that?
Pull out the calculator.
And you start plugging in all those numbers?
Yeah.
Yeah, so that's a nightmare. We don't want to do that.
Okay.
Because when we calculate integrals, we're going to have to do infinite sums, so we need formulas for how to work with these sums. So we need to figure out what this equals in general. We're coming up with a formula for this.
Mm-hmm.
Trying to figure out what this equals. Now notice, if I write this sum out twice, so let me write some other terms over here. Plus n minus 2 plus n minus 1 plus n. Right?
Mm-hmm.
Okay, so I'm going to write this sum out twice, so 2 of these sums is equal to that plus n minus 1 plus n minus 2. We'll get rid of the 4. Let me space these out a little bit. Plus 2, plus 3, plus 4. Okay, let me respace these out. N plus n minus 1 plus n minus 2 plus ... plus 3 plus 2 plus 1. Agreed? I just wrote the exact same sum twice.
Didn't we do this in discrete?
We did it, but we did it proof by induction, which we can't do in this class, so we're coming at it in a roundabout way.
Why not?
He doesn't know proof by induction, and do you know how long it took to get you guys comfortable with proof by induction? Can't just throw that on him in 10 minutes.
Okay.
So you can use proof by induction to prove this, sure, but that's because you've had lots of training with it. Okay, anyways, so agreed that this is 2 of these sums, right? You with me so far? I wrote the same thing twice.
Yep.
So now I'm just going to add up column-wise each of these, and what do I get? What's 1 plus n?
N 1 plus n.
N plus 1, right?
Mm-hmm.
What's 2 plus n minus 1?
1 plus n.
So you're first. N plus 1, and then this was plus n plus 1, plus, and I'm going to get n plus 1 over and over and over again,
Yeah.
right? So how many n plus 1s am I going to get?
N.
Same amount of n.
N. I'm going to get n plus 1. So if I add all these things up, then I'm going to get n times n plus 1.
Which is just n squared plus n, right?
Well, we'll leave it written that way. That's factored. So 2 of these sums is equal to n times n plus 1. So the sum from k equal 1 to n of k is equal to what?
N times n plus 1 over 2.
Perfect. Follow that, Jeremy?
Yeah.
Okay. There's our generic formula. Now look at this. I need to add up all the numbers between 1 and 1,000. What does it equal? Let's see. That's equal to 1,000 times 1,001 over 2.
That's pretty straightforward.
Right, so it's going to be 500. Am I doing that right? We're doing 500 times this. 5 with 2 zeros, so 500, 500. There you go.
Okay.
So you just add up all numbers between 1 and 1,000. Wasn't that slick?
Are there more complex sigmas than this?
Yes, and this was about as easy as one as we can get, just adding k.
Okay.
There's 2 other formulas that we're going to be interested in, and then we won't get more complex than these 2. But obviously there's more formulas than just this. So another one, the sum now from all the terms from k equals 1 to n of k squared, what is that equal to? That one is equal to n times n plus 1 times 2n plus 1, 2n plus 1, all over 6. Now unfortunately we can't prove that because we need to do proof by induction. It doesn't have as straightforward intuition as this one does.
Would you just square that?
1 squared plus 2 squared is not equal to 1 plus 2 squared. Very different things.
Yep. Okay.
Okay? So no, not nearly that straightforward. And then finally, the third one we'll be interested in is a cubic. And this one is, strangely enough, so the cubic is equal to the sum from k equals 1 to n of k squared.
And you can't prove that?
We did prove it in discrete math.
We did?
Yes.
Well, that's cool then. I wish I could remember.
Well, it's recorded. There's lectures.
It's
You
true.
can find it. You still have your book.
What if
Yeah.
it's rooted?
What if what?
What if it's rooted? Like the k is rooted instead of squared?
We won't be dealing with that. So these are the 3 that we'll be dealing with. Now you might be given a problem where you have to use a combination of these things.
Combination.
Yeah, so let me give you an example of a problem that you might be asked to solve. You might be asked to find the sum. Here's probably as hard as it's going to get. From k equals 1 to n of something like, let's see, 2k squared plus 3k over 7. Something like that.
Okay.
Now notice, using our rules and the basic properties of arithmetic, first off, this could be rewritten as the sum. Well, I'll just do it all in one go. I think you can follow. This is, my first term is 2/7 k squared. 2/7 is a constant, so I can rewrite that out front. 2/7. See if you can just follow this all in one go.
Yeah, I think I do.
Oops. Sorry, that was awful. You see how this is this?
Yeah, and then you apply
And
those.
then for each of these, you can apply these formulas.
Okay.
So you can deal with any third degree polynomial with these 3 formulas.
What if it gets to like 4 degrees? Will we
You don't
not
have
see
a
those?
formula for that.
And we won't see them?
No.
Okay.
No, at least not early on. Okay, did that.
So why do we need to go over sigma notation for integrals?
Because in integrals, we're going to be talking about massive sums, and it's really hard to talk about those without using sigma notation.
How are they massive sums?
We're going to be summing up infinite terms.
I thought we were looking at the area underneath 2 points though.
We are. And the way that we're going to calculate that area is by adding up infinite rectangles.
Oh, I see.
So you can make n equal to infinite? Or
We're going to take the limit as n goes to infinite. Look, we're going to get there. You'll see.
Okay.
So there's our sigma notation, right?
Mm-hmm.
So now we're going to jump back, talk about an integral, and then we'll start with 5.1 where the book goes. And I'll try and calculate some integrals by hand so that you can see it in action.
Is intuitive just like the antiderivative?
So it turns out that an antiderivative gives us an integral. We use antiderivatives to calculate areas. Now that's going to be the trick for calculating areas. First we're going to calculate them by hand the hard way, and then we're going to do the trick with the antiderivatives to calculate them the easy way. The same way that at first when you calculate derivatives, you had to use the definition of a derivative and calculate it by hand, and it took forever. And then now you use your rules, and now it's really easy.
I see.
So similar theme with integrals. We're going to do it by hand a couple times, and then I don't know if I ever make you calculate one by hand. They're harder than derivatives, but the idea isn't too bad. Okay, so now let's get to the idea of an integral and what it is. So let's see how I want to motivate this. So I've got some function, and we know how to calculate areas of very specific shapes already. You can calculate the area of a circle, you can calculate the area of a triangle, you can calculate the area of a rectangle, but that's it. So now we want something more generic. We want to calculate areas in general. So I've got some curve, who knows what it's doing, but I want to know the area under that curve between the points A and the points B.
Can you first show us how an antiderivative gets us that?
No, that will be the last thing I show you.
Oh, okay.
First you need to look, the most important thing for you right now, and possibly from these two sections, is to try and establish an intuition for what exactly an integral is. Not how you use an antiderivative to calculate one, but what intuitively an integral is. Because if you can get that, then you can always work from that to calculate the antiderivative.
Okay.
The hardest problems you're going to come across that have integrals, especially when we get to calculus, is going to be knowing how to go from the physical situation that you're talking about to the correct integral to calculate it. Calculating the integral is not going to be your hard part. It's going to be coming up with the integral that captures this information. And that requires a fundamental understanding of what that integral is. So the crucial part isn't that you know how to use an antiderivative to calculate an integral. That's the part you'll memorize, you'll know how to do that for life. The hard part, the important part, is that you get this intuition for fundamentally what an integral is. And you feel like you can now set it up yourself. So let's start by fundamentally getting intuition for what an integral is. And so here's the problem. Ignore the word integral for a second. Ignore antiderivatives, ignore calculus. Well, not calculus, we need to remember limits. Everything else kind of ignore. And here's the problem I'm giving you. I give you this shape, and I come along, okay, here's 1, here's 2, here's 3, here's 1, here's 2. I'm going to give you the area of this portion right here that we have marked out. That's your problem. Find the area under this curve between A and B, whatever those are.
And we don't even know what those points are?
No, I'll tell you those points. I tell you that exactly what A is and B is. So pretend you know A and B.
Okay.
Your job now is to find this area. Now, how could we approximate this area? Because you know right now that you can't perfectly calculate this area, but you know that you could approximate it, right?
Yeah.
And so one way that we could approximate this is, now ignore those for a second because I'm going to need you to make tick marks here, is I could take this interval, split it up into a few pieces, like that, and then create rectangles to approximate the area, right?
Mm-hmm.
Now, I'm going to talk about 3 specific types of rectangles. It doesn't matter how you construct these rectangles, which of the 3 you use here. I'm going to talk about 3 just because the book specifically mentions them. So one way we could do it is we could use what the book's going to call left-hand rectangles or something to that effect. Left-hand point rectangles. That will construct a rectangle. The question is, how tall should I make the rectangle?
As tall as A.
As tall as this point?
Yeah.
So that is called, the one you just naturally chose is using the left-hand point. Right?
Okay.
So you said this one now comes up right here, so you're saying for this one we use this one. Oops, that was terrible. Hopefully I can draw these a little better. And then for this one, you're saying use this rectangle. And then for this one, use this rectangle. And you chose to use the left-hand point to give you the height.
Okay.
That's perfectly valid. There's nothing wrong with that approach. The other one the author's going to specifically mention is we could have also used the right-hand points. So I could have used this one. I could have used this one. I could have used this one. And I could have used that one's kind of the same. Right? That was using the right-hand points. A third specific one he's going to talk about is using the middle point. So find the height at the middle point and use that. Find the height at the middle point. The height at the middle point's like right there. Use that. The height at the middle point right here is like that. Height at the middle point here drops it down a little like that. Right?
Yeah.
Okay. For each of these approaches, doesn't matter. The reason I'm telling you this is because the author is going to slowly walk you up to the idea of calculating an integral. So he's going to give you a specific curve, and he's going to tell you specifically divide it up into 4 rectangles and approximate the area using right-hand rectangles. Then he'll tell you to do it using left-hand rectangles. Then he'll tell you to do it using midpoint rectangles. And you'll calculate a bunch of them by hand.
So how do you calculate that then?
With a generic curve, you can. But if it was something like, if you gave me a specific curve, like something like 4 minus x squared.
Okay.
So if you told you to do it with this, you come up here, here's where we have 4, here's where we have 2, here's 1. It's an upside down parabola, looks like that. So if he told you to divide this up into, we'll just say 2 rectangles to keep it really simple right now.
Okay.
If he told you to divide this up into 2 rectangles and calculate it using the right-hand point, then our rectangle here would look like this, right?
Mm-hmm.
And our rectangle here, the right-hand point is 0, so it would look like that. So then what's the area? You're going to need to figure out this point. What do you get when you plug in 1 to this equation? Here's f of x.
3.
You get 3, so the height of this is 3. So this area right here is
3.
3. He'll make you do simple stuff like that.
I see.
So why is he making you do all that? I remember back when I was doing this class, I thought, why are they making me do all these stupid calculations? He's trying to slowly work you up to the notion of an integral. So
Okay.
he'll make you do it with the right-hand point. You'll see that gives you less than the area. He'll make you do it with the left-hand point, which you'll see, that gives me more than the area. And then he'll make you do it with the middle point and make you see, that gives you somewhere closer, somewhere in between. Okay. But when we're actually calculating an integral, it doesn't matter which of these rectangles we use.
Gotcha.
Anyway, so there's left hand, right hand, middle, and you can pick any point in there, use that for your height. Doesn't really matter. Just make sure you understand those 3 specific, and you'll most likely have problems related to those 3 specific. Okay?
Okay.
Okay, so from here on out, in all my talking about integrals, I'm just going to pick to always use right-hand rectangles, arbitrarily.
Okay.
Okay? And there's no special reason. It makes the math a little bit nicer than using any of the middle points to pick one of the endpoints, and we'll see how that comes out. But so now let's calculate this thing. Let me give a concrete example that we'll do, and then we'll do two concrete examples, and we'll do the generic one over there. So we'll do the concrete example, something like f of x is equal to x plus 1, and we'll do this between 0 and 2. We'll do something like f of x is equal to, maybe we'll do this between 0 and 3.
Are you saying the integral between 0 and 3?
I'm going to find the area under this curve between 0 and 3. I'm going to find the area of this curve, we'll stick with x squared minus 4, that's a good one, between 0 and 2. And then I'll do it in some generic case, f of x. So I'm trying to help you understand the generic formula. So we're going to do two concrete examples and then the generic formula, and hopefully the generic formula sticks.
Okay. Don't you put open intervals around your 2 points, or does that not matter?
I'm just putting that up there as information for myself.
I see.
So here's essentially what I'm calculating if you want a formula. I want to calculate the integral from 0 to 3 of x plus 1 dx. I want to calculate the area of this between 0 and 3.
Okay.
So let's draw a picture of what I'm doing. 1, 2, 3. X plus 1, its y-intercept is 1. So this is just going to be a straight line, goes to this point, goes to this point. Well, we can kind of just mark it out, all the points, and try and force it to make sense. So here's the function we're talking about, and I want to calculate the area starting here and ending here of this function.
Gotcha.
Okay, so why are we starting with such a simple example? Because notice this happens to be a shape that you could easily calculate the area of, right?
Yeah.
We know that the area of this chunk right here is 3, right?
And then
And then this one is 3 times 3 divided by 2 is 9 halves.
Yeah.
Okay. So we know how to calculate like that. But now let's think about using the rectangle approach. If we use the rectangle approach, here's what I'm going to start by doing. I'm going to divide this up into a bunch of rectangles. So, and we're going to use right-hand rectangles. So I'm going to have rectangles like this. Sorry, I meant to just divide like that. Get a few of them in here. And I said I'm just going to arbitrarily choose a right-hand point. Okay? Now I'm going to divide this up into n even sections.
N even?
Okay.
Yes, so this, I'm pretending each one of these chunks are the same base, even though my picture's blank, is what I'm trying to say.
Okay.
And I happen to divide it up into 8, but in general, we're going to say I divide this up into n sections. So what is this distance right here if we have n of these?
X.
Let's actually count it for how many we have. Pretend that these are evenly divided. What's this distance right here?
1/8.
So remember all the way to here is 3. So what's this distance right here?
0.5. Do I have that messed up?
Look, I have a total distance of how much?
3.
This is what portion of that distance?
1/8 of that distance.
So it's 1/8 of 3. So this is, oh my goodness, 3/8.
What? That doesn't add up though.
3/8 plus 3/8 plus 3/8 plus 3/8 plus 3/8 plus 3/8 is 3.
Oh.
If you have 3/8 8 times,
Yeah. Okay. I'm sorry.
Okay.
Okay. I got you.
goodness. All right. So this right here, this distance in this very specific case was 3/8, right?
Mm-hmm.
Yeah.
Now pretend I would have had n intervals instead of just 8. What would this distance be?
1 over n.
Or something over n.
When n was 8, we had 3/8.
Mm-hmm.
If n was 100, what would this distance be?
3 over 100.
Okay. So if I split this up into n, what's this distance?
3 over n.
3 n's.
Okay.
Make sense? That is the base of the rectangle. And that's the base of all my rectangles.
Yeah.
Notice I'm trying to calculate the area of all these rectangles. So I need to do base times height for all these rectangles.
Okay.
Okay? So I'm trying to do the sum from k equals 1 to n of base times height for each of these n rectangles.
Okay.
Okay? So the base of each of these rectangles
That's 3k.
is 3 over n. No, not k. 3 over n. It's the same no matter what. It's constant.
Mm.
Okay.
Make sense so far? Times, now we need the height.
Okay.
What is the height of the what's the height of the rectangle? It's the height at the right-hand point, right? So pretend for a second that this point right here is 8/3.
Yeah.
How high is this point? What's the height of this?
8/3 plus 1.
1 and 8/3.
So it 1 plus 8/3, you're right, but I'm going to just call it f of 8/3 for now, right?
Yeah.
Okay, notice what's the coordinates now of this point? The next point, in the case I have drawn here, where we're talking about 8s. So we know the coordinates of this point are 8/3. What's the coordinates of this point?
2 8/3.
2 8/3.
How did he do that?
We've gone 8/3 over twice.
Oh. I see.
So the coordinates of this point are 2 8/3. What's the coordinates of this point?
3 8/3.
3 8/3. What's the coordinates of this point?
4 8/4.
4 8/3.
Thirds.
So if we were writing, let me write the area for the specific picture we have, and then we'll write the area with ends. Maybe that will help a lot.
Okay.
So I'm going to do this actual sum of the actual picture that we have here, and then we'll bump it up to the nth case. You with me? So in this case, we're doing a sum from k equals 1 to 8 of area of the rectangle is base times height. So our base is 8/3 times what's our height? Our height is going to be f of k times 8/3. For our first rectangle, what's the area of this rectangle?
8/3 times f.
8/3 times f of 8/3, right?
Yeah.
What's the area of this rectangle?
8/3 times f of 8/3.
8/3 times f of 2 8/3.
Yeah.
So when you notice what this is equal to. Let's write it out. This is 8/3 base times f of 8/3 height. Plus 8/3 times f of 2 8/3. Plus dot dot dot. And our last one will be plus f of, we're going all the way up to 8. So f of 8 times 8/3. Or 3. Oops, I forgot my
Yeah,
8/3
times
up front.
8/3.
You follow me on that?
Yeah.
So you see how this captures this formula? And notice I can rewrite this last term as plus 8/3 times f of just 3, which is our endpoint. So there's always a quick sanity check there to make sure you have the right formula. Plug in the case where k is equal to our last number 8, we better get f of our last term. Okay, anyways, here's what it is for 8. Now what if we would have split this up not into 8 pieces, but into n pieces? Any number n.
Okay.
N even pieces. Then we'd be talking about the sum from k equals 1 to n. Instead of 8/3, we'd have
N/3.
n/3 times f of
K times N/3.
k times n/3. Perfect.
Okay.
You with me?
Yeah.
And we can use the fact that we know what the function is. This is the same thing as the sum from k equals 1 to n of n/3 times f, when we plug in k times n over 3 into this, then we get k times n over 3 plus 1, right?
Mm-hmm.
Just plugging this into f. Here's f.
Why are you plugging it into f?
We're going to evaluate this thing. We can't just leave it like this. Look, notice up here we don't have a number yet.
Yeah.
I still need to figure out what this is and what this is and what this is, and then we can calculate it and finally get an actual number when it's all said and done. Right?
Okay.
So I need to evaluate what this function is. We know what the function is, so use that information. I know that f is this function.
Mm-hmm.
So, you good with going from here to here?
By using the integral, not just the function. Oh, never mind.
The function's right here.
Yeah.
Okay, so just using the function. Okay, and then, so from here we can do some basic algebra.
Okay.
Right? This is equal to, maybe I'll split this into two sums really quick. The sum from k equals 1 to n of this first term. This first term is going to be k times n squared over 9
Yeah.
Mm-hmm.
plus, and I'm going to split this into the second sum. The sum from k equals 1 to n of, we have n thirds times 1. Right?
Yeah.
But that's just a constant.
Right, so we're going to evaluate some of these things now. So this is equal to, oops, that's supposed to be an equal sign, sorry. So this is equal to, pull out the k-nights. So we get k over 9 times the sum.
Why can you put the k lunch above the end?
Oh, thank you. Because I was thinking about the n is variable, which is wrong. K is my variable. Good eye. K equals 1 to n.
Wait. It has to be k over 9, right?
No, I pulled out the 9. 9's a constant. Pull it out.
But it's dividing both of those terms.
It still is. If I multiply this back in, it's still
I
dividing
see.
both those terms.
I see.
Okay. Plus, what does this equal? We know how to evaluate that.
N squared over 3? Because it's n times.
We have n thirds n times. We have n thirds plus n thirds plus n
N
thirds.
squared over
So
3.
n squared over 3. Perfect. Right?
Mm-hmm.
Which is equal to, we now know how to evaluate this thing.
Yeah.
So this is n squared over 9 times, when you evaluate this thing, you might have forgotten the formula, but you'll learn it. It's n times n plus 1 over 2.
Mm-hmm.
That's what we just did, right?
Oh, yeah.
Plus n squared over 3. Right?
Okay.
Let's get a common denominator and put these things together. So this term over here is going to be, this term is going to be n cubed times n plus 1. And then over 18, but we're going to write the whole thing over 18. I'm going to get a common denominator.
So that's 6n squared.
Exactly. Plus 6n squared. Good?
And that's our answer?
No. We haven't introduced any calculus yet. Everything we've been doing so far is just calculating the area of n rectangles under this curve.
Okay.
That's all we've done so far. So now let's just multiply it all out and see what we get. So I'm going to get n to the 4 plus n cubed
Mm-hmm.
plus 6n squared all over 18. Okay, that is the same thing as this simplified, right?
Okay.
Now, it doesn't matter what n I choose. If I make n 100, yeah, that gives me a better approximation, but it's still not perfect,
Okay.
Yeah.
right? If I divide that up into 100 rectangles, it gives me a better approximation, but it's not perfect. If I divide it up into 1,000 rectangles, it's still not perfect. How big do we need to let n be to make this perfect?
Infinity.
Infinity.
But how does that
So
work?
now, here's where the calculus comes in. I need to calculate the limit as n approaches infinity of this sum.
Oh, I see. Okay, let's do it.
So I need to calculate the limit as n approaches infinity of... We completely messed up.
What?
Oh goodness. Should have caught this way earlier. This distance is not 8/3, it's 3/8. We had it right the first time I wrote it, then I erased it at one point and rewrote it, wrote it wrong.
Well, you
Now-
said let this point be 8/3, and I was like, okay.
Yeah.
No, I'm saying if we divide 3 into 8 pieces, it's 3/8.
Yeah.
And so now this is 2 3/8, and this is 3 3/8.
Which makes that 3 over n.
And even over here, I said notice when you cancel it out, you get 3, which, no you don't. Not unless that's 3 over 8. I can't believe we left that up there. Okay, oh my goodness. Everything should be 3 over 8, not everything over 3. I can't believe we did that. Can't believe none of you caught it, even when I talked about it there. Does it make sense to you why all of these should have been 3 over 8?
Yeah.
It makes, yeah.
We're taking 3 and we're dividing it up into 8 pieces. I mean,
I noticed it, and I thought that, because it's new stuff, I thought that that's how
nope,
it was supposed
always
to
point it out if it doesn't make sense. Okay, so
Okay.
this should have been 3 over n. No. Or,
N over
it
8.
should have been 3 over n. It should have been n over 3, it should have been 3 over n.
What? Oh.
Yeah.
You take 3 and you divide it up into n pieces. You take 3 and you divide it up into n pieces.
So you can only do this if you know your a and b, right?
Yes.
Okay.
This should have been 3k over n plus 1. And our algebra is just going to blow up from here. So we way messed up, right? Absolute nightmare.
Yeah.
That's on you guys. I'm just a teacher.
Okay.
Okay, this marker's kind of dying on me. Maybe this one's better. What a waste of time. Okay, restart. Okay, this is now equal to. Do we have it all written right? Yes, we have it all written right. Okay, so calculating these sums now. So this is equal to the sum from k equals 1 to n of
9k over n squared
9k over n squared
plus.
plus 3 over n, right?
Mm-hmm.
Which is equal to, split this up into two sums. So we'll have 9 over n squared when we factor it out of there.
Mhm.
Then we have to sum up those k's. When we sum up those k's, we'll get n times n plus 1 over 2. So we're taking care of this portion so far.
Okay.
Now I need to sum up these. If I sum up 3 over n times, what do I get?
3.
Plus 3. Perfect.
Mhm.
Okay, this is equal to now, distribute out the top, we're going to get 9n squared plus 9n all over n squared plus 3.
What about your 2
Oh, did I miss a 2?
2
in the
n
denominator?
Oh, thank you. Thank you.
Okay.
Okay, good, because I can already see it popping out. I'm feeling much better. Wow. Alright, so now that's our area for n rectangles.
Can't you
But-
simplify?
It's fine how it is, you'll see. It's just because I know where I'm going that I'm leaving it like that.
Okay.
So now where the calculus comes in. We need to calculate the limit now as n approaches infinity of this thing. That would be calculating the sum of infinitely many infinitesimally small rectangles, right?
Mm-hmm.
So I want to calculate the limit as n goes to infinity of this thing right here. Which is equal to the limit as n approaches infinity of that whole thing. Right?
Mm-hmm.
And we know how to calculate these limits.
Yeah.
Let me rewrite this one more way just because I think it'll help take the limit. Since we haven't seen this for a little bit. I'm going to split this into two fractions. So 9n squared over 2n squared is just going to be 9 over 2. Plus 9n over 2n squared is going to be 9 over 2n. And then plus 3 is still going to be 3. You follow what I did there?
Mm-hmm.
Okay, now take the limit. What do we get?
9 over 2n, so 2 times infinity,
What happens to this term as n approaches infinity?
gets closer and closer to 0.
Smaller.
And in the limit, it is 0, right?
Yeah.
So the limit of this is 0. What's the limit of 3?
When it goes to infinity, it doesn't matter, does it?
Right, so what's the limit of a constant?
0.
What's the limit of a constant?
Just the constant?
Just the constant.
Yeah,
What does 3 get closer and closer to as n approaches infinity?
3.
3. Gets really close to 3. 3 gets as close to 3 as 3 could ever get. Okay, so what's my limit now?
9 halves plus 3.
9 halves plus 3. Now notice, we already knew from looking at the picture before that that was the answer. The 3 was this area down here. That's the 3. And the 9 halves was this top rectangle. Or top triangle.
Okay, I see how it's working now.
So we just barely calculated an integral by hand.
Okay,
We just barely calculated this integral by hand.
yeah.
Good?
Mm-hmm.
So I'm going to do one more example calculating an integral by hand. And then we'll move on to giving you a generic way to look at integrals.
Okay.
Good?
Yeah.
Yeah, we'll erase it all. I think we'll be okay. So next, what was the function I said I'd do next? X squared minus 4. Okay. So now we're going to do x squared minus 4. Between 0 and 2. You need to know where it's between, otherwise you're in trouble. So,
It's at minus 4.
oops. I meant to do this. Thank you. So, when we plug in 1, we get 3, right?
Yeah.
So it should look roughly like this, something like that. Okay, so this is the area now that we're trying to calculate,
Mm-hmm.
right? So I am looking for, so we're trying to calculate the integral from 0 to 2 of 4 minus x squared dx. So this is equal to the limit as n approaches infinity of the sum from k equals 1 to n. We're going to sum up n rectangles.
Mm-hmm.
And in here, I'm going to have base times height. Right?
Is it always base times height?
Yep, that's the area of a rectangle, base times height. Now this time I'm actually going to do height times base because that's kind of how it's written here. Height times base is one way that you can think about what that integral is saying. dx is an infinitesimally small change in x, and then f of x gives you the height. Height times base.
Yeah.
An integral is an infinite sum. So just follow the integral. We're going to do, I need to do f of some point. We've got to figure out what that point is. Times the base, and we got to figure out what the base is. If I divide this up into n pieces, n equal pieces, what is the width of my base going to be?
2 over n.
2 over n. We're going to take 2 and divide it up into n pieces. So that's my base,
Yeah, just like we did before.
just like we did before. What is my height going to be now? It's going to be f at some point, so I got to find my right-hand point for an arbitrary rectangle. Now if you're stumped here, The good thing to do is to just draw a couple and see where your right-hand point is.
So we actually have to go to a point to figure out the height? Is that what you're saying?
Yeah, we have to pick the right-hand point of each rectangle. So
But
I
you're
got to
doing
plug
the
in this
ends.
right-hand point, then this right-hand point, then this right-hand point, then this right-hand point.
Can't you solve it for n?
Yeah, but you're trying to solve it for n, are you not?
N is
And
just
rectangles.
some number.
N rectangles, right?
Oh, yes,
Yeah.
for n rectangles.
Why are you solving it for 4?
Well, I'm saying if you're stuck on how to figure out this point, plug in a particular case and see what the right-hand points are.
Okay.
And then hopefully you can see a pattern.
So you're saying,
So what's the right-hand point of this rectangle in this specific case?
the right-hand point?
Yeah, what's that point?
1/2.
1/2. How'd you get that?
It's half between 1 and 0.
Yeah.
Okay, I'm gonna write it as 2/4, but 1/2 works.
2/4. Why 2/4? Oh, because of n. Yep.
And then what's this point?
1.
1 or 4/2. Or 4/4, I mean.
Mm-hmm.
What's this point?
6/4.
6/4. And what's this point?
8.
8/4. Right?
Yeah.
So for my first rectangle, it's 2/4. For my second rectangle, it's 4/4. For my third rectangle, 6/4. For my fourth rectangle, 8/4.
Mm-hmm.
So in general, what's the right-hand point going to be now if we divide this into n pieces? So now pretend I divide this into n pieces. What's my first point going to be?
2/n.
2/n. What's my second point going to be?
4/n.
Etc.
Yeah.
Until my last point is going to be,
8/n. Or
no, my very last point if we have n of them. Remember now, we're talking about n rectangles, so there's
equals
tons.
2.
2 or 2n/n if we follow the pattern, right?
Yeah.
We got 2/n, 4/n, 6/n, 8/n, 10/n, 12/n, 14/n, and we're going to follow that pattern all the way to 2n/n,
Okay.
right?
Mm-hmm.
So, for my first rectangle, for my second rectangle, for my third rectangle, and for my nth rectangle, that was my right-hand point.
Mm-hmm.
Yeah.
Just rewriting these exact numbers.
Mm-hmm.
So for my kth rectangle, what is the right-hand point?
K times 2/n.
K times 2/n. Follow that?
How is that the height?
No, f of that is the height.
Oh.
This is just right-hand point.
Mm-hmm.
So I told you I'm going to arbitrarily just use right-hand point every time. We could have instead been calculating with left-hand points, and it would work just as easily, or just as well. We could have calculated using midpoints, and it still would have worked.
Okay.
So basically, it's f of k times your base times the base.
It's base times height of your kth rectangle.
I'm saying for the generic across the board, is it always f of k times your...
It's f of some point in your rectangle to get the height
Yeah.
times the base. It's height of rectangle times base.
Would there
We happen to be always using the right-hand point. I could have just as easily always used the left-hand point. That would change what this looks like, but when we take the limit, we get the same thing.
So it's different if you do the left-hand point?
The math inside of here is going to come out different, yes.
But you always end up with the same thing?
But when you take the limit, you'll get the same thing.
Okay.
Make sense? Okay. So that is the hard part. Going from here to here, this is always the hard part.
Yeah.
And that is what I mean when I say that it's about going from some physical situation to the integral that represents that physical situation. That it helps to have an understanding of what the integral is. And once we get to here, we should be pretty well set.
I think so.
So now we can just calculate this. So this is the limit as n approaches infinity of the sum from k equals 1 to n of, now we plug this into our equation,
Mm-hmm.
of 4 minus, we have 2k over n is another way to write that, right?
Okay.
So 2k over n squared is going to be 4k squared over n squared, right?
Mm-hmm.
Times 2 over n. For the base.
Do you distribute the 2 over n?
Base times height. Yeah, I'll distribute it in.
Okay.
Oh, sorry. Yeah, I see what you're saying. Let's just do that, and we'll do that. That's what it should look like. Okay. So this is equal to, I'll distribute and split up the sums at the same time.
Okay.
Limit as n approaches infinity, now we'll do that, of, we have 8, well we can also add this up as we go. So 4 times 2 over n is going to be
8 over n.
8 over n. Add that up n times, what do I get?
Add it up n times. 8.
8. So when I take this to this and take its sum, then we get 8, and now I'm going to minus the other sum. So minus the sum from k equals 1 to n of this term.
So 8k squared.
So I'm going to pull out all the constants, so I'm going to pull out 8 over n cubed out front.
Oh, I see.
And what are we left with?
K squared.
Does that make sense, everything that we did there? Kind of a lot of algebra in one go.
Where did your n go? That was under the 2.
I distributed it. So for here, when I distributed it to this term, that one's right there. When I distributed it to this term, notice that it gave us 8 over n, right?
Yeah.
But then when we added that up, we had n of them. So I added up this term in one go for just 8.
What do you mean?
Okay. Too much one go. So let's just write this out. So we have the sum from k equals 1 to n of 8 over n minus the sum k equals 1 to n of 8k squared over n cubed. Okay, good with that? Okay. When we calculate this sum, what do we get? Well, it's 8 over n plus 8 over n plus 8 over n times.
Just 8.
Just 8. So that's where that 8 came from before. Minus, and from this we're going to factor out 8, 8 over n cubed, right? We factor that out, and then we just sum up the k squared. And we have our formula for that. You're not expected to have that memorized, but what is it? K times,
No, n times.
or thank you.
N times n plus 1 times 2n plus 1
Yeah.
over 6.
Thank you. And that's what we're calculating, right?
Yeah.
Okay, so this is equal to the limit as n approaches infinity of, notice, if when you take your limit you're not getting a number, you mess something up. Just keep that in mind.
When you're not getting a number?
Yeah, when it's all said and done, this is a definite number. So if this is blowing up to infinity, or if it's coming out 0, I did something wrong.
I see.
In other words, a lot of n should be canceling out to leave me with just numbers or zeros. Anyways,
Okay.
let's calculate this now. This is the limit of 8 minus, now we gotta distribute this massive beast. Alright, so n times 2n is going to be 2n squared, 2n cubed, 16n cubed. So that was doing these two. With me so far?
Mm-hmm.
Now, when I do these two, I'm going to get 2n, but when I do this, I'm going to get another n, so I get 3n for my n's, but that becomes n squared, so that becomes 24n squared. And then finally for the 1 and the 1, times n times 8 is going to be plus 8n.
Yeah.
All over 6n cubed. With me?
Yep.
And this is equal to the limit as n approaches infinity of a field is 8 minus, now we'll split this up into 3 separate terms.
Okay.
So 16n cubed over 16n cubed is
8/3.
16n cubed over 6n cubed. Oh, I said it wrong. Thank you. Minus 8/3, right? Minus, because I need to distribute the minus to every term. 24n squared over 6n cubed is
4n.
4 over n.
4 over.
4 over n.
Yep. Plus, and then 8n over 6n cubed is
4 over 3n.
3n.
perfect. Okay, now take our limit. The limit of 8 is
8.
8. The limit of 8/3 is
8/3.
8/3. The limit of 4 over n is
0. 0.
so 8 minus 8/3. Or, let's see, 24 minus 8
16.
is 16
Over 3.
over 3.
6/3.
Now, I'm going to do some of the easy way really quick, just to make sure that we did it right.
Okay.
So, give me just a second here. Okay, we did it right. There you go, you just saw the shorthand way of doing this.
You just like.
But you want us to do it that really long way?
Yes,
Okay.
I want you to have a fundamental understanding of what these things are, because there's going to be points where you don't just use integrals to calculate areas. There's going to come a point where you use integrals to calculate, areas of surface areas in 3 dimensions. There's going to be a point where you're using them to calculate volumes. There's going to be a point where you're using them to calculate velocities from accelerations. You use these all over the place. And so
Okay.
it helps so much to have a fundamental understanding of what these things are when you calculate by hand. Just can't overstress that. There's so many points where, like I did a lot of tutoring when I went to college with my fellow classmates. And there were so many times where I'm having a conversation with them, trying to explain something to them, where it's obvious that they just memorized the formulas that they needed to get the answers and didn't really understand fundamentally what we were talking about. And that was our holdup. They need to fundamentally understand the concept.
Yeah.
And they kept trying to get me to just give them the formula. And there's this weird back and forth where there's no formula. You just need to understand that this is what's happening. Or it doesn't matter what the formula is, you just need to understand what's happening. And so many conversations happen like that as you get deeper and deeper into mathematics. Your ability to rely on a memorized formula becomes less and less and less. You just need to fundamentally understand what it is and just think about it. Right? It's like going from when I ask you to calculate a derivative to when I ask you to calculate the minimum surface area that you can use to get a cylinder can that holds 500 milliliters of liquid. One of them you can just use a formula. The other one, if you don't fundamentally understand that a derivative is capturing how something changes with time, well, that's one way you can use a derivative, then you can't solve those types of problems. It's not enough to just have a formula. You need to understand a derivative to solve that problem. Right? Because I didn't just give you the formula to take the derivative of. You had to come up with that.
Yeah.
You had to intuitively understand, okay, I'm trying to minimize the surface area, so I need an equation that gives me the surface area, and then I need to look for a local min. You see how that's a deeper level than just can you calculate the derivative of some formula?
Yeah.
Same thing's going to be happening here. There's going to be problems where understanding what an integral is going to make so that you can solve those problems that aren't just stupid trivial problems. Where it's like just calculate the derivative of this equation. There's calculators on lines that can do that. If that's all you can do, I can use a calculator online that can do that and replace it like that. But a calculator online can't tell me how to go from some physical scenario to the equations I need to use to solve that.
that makes sense.
That's where the human comes in. That's where that intelligence comes in. And it's developing that ability that's so hard and so useful. That's why anyone will pay, like, for a physics major. You go major in physics, you can program anywhere you want. Because it's that ability to think that people care about. I know a couple company owners who said they'd easy take, running tech companies, who said they'd easy take a math major over a CS major. Because the math major had a better ability to do this thing. So this skill, this ability to go from some physical scenario, some problem you're trying to solve, to the abstraction that you need to use to solve that problem, it's huge. It goes way beyond basic calculus I'm talking about.
And that's all physics is, right?
That's all a lot of things are. A lot of my job as a programmer is I have some problem I need to solve. I need to design some abstraction that solves that problem. And I need to keep it as simple and clean as possible. And if I get caught up in the nitty-gritty details of that one problem, and I come up with all this code which solves that one problem, and then some other problem comes along that's very similar, but not quite the same, if I made this so specific to this one problem, then I can't reuse this for this. But if I kept it nice and generic, and I recognize what the problem's really asking on a higher level, it saves me a lot of work, and that's what good developers do. They design reusable abstractions.
I see.
So it's applicable everywhere. And that's a lot of thinking, is just abstracting. What's the minimum abstraction I need to capture this concept? So it's crucial to fundamentally understand what something is, rather than just relying on, oh, I know the formula to calculate that. So does a computer. Okay, anyways, so we calculated another one by hand, right?
Mm-hmm.
Okay, so now I'm going to try and leave this up here while writing a generic situation underneath so that you can see the parallels.
Okay.
So now we're going to do generic. I'm calculating, I have some curve, I don't know what the curve is now, some curve f of x. And we're going to go from A, I probably shouldn't have started as 0 on both those. I think you'll still be fine. A to B, and I need to calculate the area now between A and B of this function. This function's f of x. You with me?
Yeah.
So that area is going to be the limit. As n approaches infinity, we're going to take infinite rectangles, right?
Mm-hmm.
Of the sum from k equals 1 to n
Of f of,
we'll figure out what that right hand point is generically, times the base, we'll figure out the base generically.
Okay.
Okay, so we're going to pick some generic rectangle in here and just talk about its coordinates so that we can do this in general. You with me? So for some cake rectangle, what is the base going to be? Well, what is this total distance?
B minus A.
B minus A. And we're dividing B minus A up into how many pieces?
N.
N pieces. Your base is always B minus A over N.
And you put that right there, right?
So B minus A over N is always our base.
Okay.
You with me?
Mm-hmm.
Now the height, we need to figure out what the right point is right there.
Mm-hmm.
Now for our first triangle, let's do our first triangle and our second triangle, and then we'll do our kth triangle.
You mean rectangle?
Rectangle, thank you, yes. So we'll do our first one, our second one, and then over here we'll do it for our kth one. Does that make sense what I'm saying?
Yeah.
So for my first triangle, what's this right hand point?
1 times b minus a over n, right?
What's this distance?
B minus A over N.
What's this distance?
A minus 0,
Which is?
a.
So what's this distance?
A plus b minus a over n. I see.
So it's just B over N.
So that's,
No, it's not.
okay. No. Okay. So that's the coordinates of this point, right?
Mm-hmm.
For our first one. What would it be for our second one now?
Just 2. a plus 2 times b minus a over n.
Perfect. And for our caked one, this point, what would that be?
A plus k times b minus a over n.
Perfect. That's exactly what it is.
And in all the situations, a with 0.
It happened to be with the two we chose, so sorry about that. I should have.
But yeah, I see
Been
why
more
it works
creative.
now. Okay.
So this right here is calculating an integral.
Can you convert that to the integral notation?
This is equal to the integral from a to b of f of x dx.
Okay.
Now, quick note of warning that you can almost forget, but I just want to be very, very clear. Technically, this is not the exact definition of an integral.
Okay.
We were a little bit too restricting.
Too restricted.
Yeah, so I'm
Okay.
giving you something that's this when technically the definition of an integral gives you this. And I restrict it to just this.
Why?
Because it's good enough for the cases that we're talking about. So we'll come across the exact definition of an integral in 5.3, and you'll see how it's a little bit more generic than this,
Okay.
but how this is still just a special case of that, and it works.
Gotcha.
And this is a formula I use almost every time I go to calculate an integral by hand.
This formula.
Yes.
Okay.
So it's almost the exact definition. Not quite. Technically, we need to make it a little bit more generic. Here's where we need to make it a little bit more generic. Remember how I kept telling you the right-hand point or left-hand point or midpoint doesn't matter? It doesn't matter which of those points you use. That's the only thing that changes. So we say pick now any point in between. Call it c sub k. So if we're talking about the caked triangle, then we say pick any point between this point, or any point in between. We happen to always choose the endpoint. But you can pick any point in there, call it just c sub k, and then just replace that with c sub k. That's a generic formula.
F of c sub k?
Yes, where c sub k is any point in between. We happen to always choose the right-hand point. You can use the right-hand point, you can use the left-hand point, you can use the middle point, you can use any point.
What would the left-hand
calculate
point look
that.
like? B minus that?
Shifting over one. So now we use this point instead of this point, this point instead of this point, this point instead of this point.
Oh, I see.
So we just shift backward.
Everything, okay.
Okay, so it can change a little bit, but if you just replace that with the generic c sub k, where c sub k is any point in between, we always use the right-hand point, but if any point in between, that's the full generic definition of an integral. We didn't have to use the right-hand point, this is always using the right-hand point. That's the weird restriction that we're putting in here. Okay. Right? Maybe we're calculating some weird integral where the right-hand point happens to not be defined.
And so we have to do the left or the
And so you have to, who knows? Weird scenarios. But the point is, vast majority of the time I go to calculate an integral by hand, I just go to that exact equation. You with me?
Mm-hmm.
Okay. So, there we go. I gave it to you kind of all in one go. An integral. There it is. Calculating it by hand, there it is.
Okay.
And we'll learn the formulas later. So now we'll go through what the book wants us to go through. Pointing stuff out. But what you already did is way harder than anything the book has you do. 5.1 is just going to make you do a bunch where it just says use 4 rectangles to approximate the area. So it's going to be really simple stuff. So I'm not too worried about covering a bunch of that. I think you guys can get through 5.1 pretty much on your own.
What's 5.2?
5.2 starts out by introducing sigma notation.
Okay.
So you'll have a bunch of problems with sigma notation, saying like expand this out or whatever. And so I'm just now going to go through the highlights of what the author wants mentioned.
Okay.
Because we also know that an integral, even though We don't know how to relate it to area yet. I'm going to try and make that connection now here in a second. But we also know that somehow an integral of velocity gives position, or that the integral of acceleration gives velocity, right? Because an integral somehow undoes a derivative.
Mm-hmm.
And how does that work? How can we view an integral as undoing a derivative, or a derivative as undoing an integral? That shouldn't really make any sense right now, right?
Yeah.
How are areas and slopes somehow inverses of each other? What? That's weird.
And we get into all that?
Yeah, we're going to try and make this appeal to your intuition.
Awesome.
So, first thing I'm going to do, distance traveled, I'm going to try and make it appeal to your intuition how if we were to integrate velocity, we would get position. Okay?
Okay.
So what I'm going to graph now is a velocity function, not a position function. Now I don't care what velocity function we use. Let's just keep it something simple. We'll just use velocity at time t is equal to, what should we say? 5 plus 2t, something like that, meters per second.
Okay.
Something like that. Let's actually do 1/2 t. That way it doesn't grow so fast so I can make my picture a little better. And let's replace that with like a 2 so I don't have to go so high. Okay. Yeah, do it for the picture. Okay, so we have 1, 2, 3, 4, 5. This should be funny. 1, 2, 3, 4, 5. Something like that. Okay. And so we're going to use this and we're going to talk about how our position changes over some interval of time, right? So I want to know how my position changes from 0 seconds to maybe I'll write this 0 less than or equal to t less than or equal to 2. Let's see how our position changes over the first 2 seconds.
Okay.
And try and get intuition for how an integral could give you this. So I only care about over 2 seconds. Let's actually go 1, 2, 3, 4, 5, 6. We'll do it over 6 seconds.
Okay.
Let's have one that actually doesn't start 0. Let's do 1 to 6. Okay?
Okay.
So what does this function look like? It goes through the point 2, then we go over 2 and up 1, right? Then we go over 2 and up 1. Then we go over 2 and up 1. Did we cover 6? 1, 2, 3, 4, 5, 6. Okay, there's 6. So that should be enough. Try and create something half decent. Okay, so we're talking about from here to here.
Yeah, it would sound
1, 2, 3, 4, 5, 6. Dotted lines will help fix our view. Right?
Yeah.
Okay. Yeah, which do you want this one? You get the problem. So here's 1, here's 6. We want to see the change in this function's position if this is the velocity, which is this line, right? Now, this axis right here is time, right? And this axis right here is your velocity.
Yep.
So how fast am I going at 6 seconds? I'm going 5 meters per second. So this is meters per second, maybe to do it that way. This is meters per second, and this right here is seconds. Does that make sense?
Yeah.
Yeah.
Okay, so now we know what an integral does. An integral is calculating the area under the curve, right?
Mm-hmm.
So we're splitting this up into a bunch of rectangles. So let's draw an arbitrary rectangle here. We'll follow the convention of using the right-hand point. But some arbitrary rectangle here. Good?
Mm-hmm.
Now, what is that right there? That is a small interval of time, right? Delta t. That's our small interval in time, our small change in time, delta t.
Okay.
That's the base of this thing.
Mm-hmm.
And what is the height of this thing? Well, we need to put a point in here really quick. We'll call this point right here t naught. And then this distance right here we call delta t, is the distance between, right? So then the velocity at that point, the velocity is v of t naught.
Yeah.
That's the height of this thing, right? Now notice, on this teeny interval, as we make the interval smaller and smaller and smaller, using this as the height, using this for our velocity, for this whole interval gets a better and better approximation, right?
You're saying just do it smaller, gets better and better.
I'm saying right now we're assuming that they have this velocity, which is their velocity at the endpoint. We're assuming they have that velocity over the whole interval, which they don't. They sped up a little bit.
Yeah.
But we're assuming, no, they had that velocity over the whole interval, right?
Okay.
Sorry. Maybe I should have said this real quick. Notice what the area of the rectangle gives me really quick. It gives me v naught of t times delta t, right? Which is equal to velocity times time gives us,
I don't know what velocity times time is.
if I am going 100 meters per second, and I do that for 2 seconds,
Oh, speed?
No, position.
No.
displacement,
Displacement.
Why is
position, change in position, displacement, 200 meters,
Yeah.
right? Rate times time gives you distance.
Distance? Displacement is distance, okay.
Technically, displacement and distance are almost the same thing. We'll get to that technicality.
Okay.
So I should say displacement. Okay, velocity times time gives you displacement. Right?
Yeah.
So this gives me a small change in x.
Small change in time? Is that what you're saying?
Oh, sorry. S being our position function. Because we have s for seconds, so I'll use SEC for seconds here. And then I'll say a small change in our s function. Because remember, we have s of t gives us position, so it's equal to something. V of t gives us velocity, and then a of t gives us acceleration. And we know that ds dt is equal to this thing.
Yeah.
Okay, that's the s I'm talking about. So notice that velocity times time gives you distance. So on this small interval, delta t, I have approximately this velocity on this whole interval.
Yeah.
And so this is approximately the distance I go on that small interval. Delta s, which is the area of this thing.
Okay, but aren't we looking for the area of all the rectangles? Like, why do we care about that one?
We're just doing it for a generic one first.
Okay.
Because now I'm going to sum them all up.
Sum all of delta s.
Sum up all these little rectangles. The point is, what do these little rectangles give me? A little bit of displacement.
Yeah.
So if I sum up all the rectangles,
It gives you all the
it
displacement.
gives me all the displacement, which is the point. We already showed how velocity is the slope of position.
Yeah.
What I'm trying to get you to connect now is, if you plot velocity now, the area under velocity gives you position.
The position function or the position?
The position, same thing. Position function gives you position. That's
Yeah,
right.
but how do you, but when you do the integral stuff, you only get a number. How do you get the function out of that?
Oh, okay, I see your confusion.
Oh, okay.
So this is going to give me the distance from 1 to 6.
Yes.
So this is going to give me the exact same thing as s of 6 minus s of 2, or s of 1.
Yeah.
So my integral, here's the correct way to write it. My integral of dt with respect to t from 1 to 6 gave me that.
Oh, I see. So you're not getting the function.
The point was to try and connect with your intuition, how when we were looking for the velocity at a time, we looked at the slope at a point of this function. Take this function, look at a slope at a point, that gives you the velocity at that time.
And if you take the integral,
Now if we look at this function, and we look at the area under that function between 2 points, that gives you the change in position between those exact same points.
Can you do that between velocity and acceleration as well?
Yes, same exact connection holds.
Awesome.
So we can also say that this is somehow capturing the same information as the derivative of s with respect to t is equal to bt. This is somehow capturing similar information, this and this.
Okay.
Similarly, yeah, we could say something similar. The integral from a to b of our acceleration function would be our velocity at b minus our velocity at a. And that has to do with the fact that, once again, the derivative of velocity with respect to time is our acceleration function. Yes, those are very closely connected.
Okay.
Okay? So we're not necessarily just talking about areas, right? Because we can integrate on velocities to get changes in position. Same way we can differentiate on position to get specific velocities.
Gotcha.
So there's that connection. That make sense?
Can we finish going and doing this?
Finish going and doing this.
Finish the problem?
Oh, you want to actually calculate it all out?
Yeah. I mean, it would be helpful just to see a position and velocity instead of just a simple f of x.
I mean, we can calculate it all out if you want. So here's what we're calculating. We know that this is equal to the limit as n approaches infinity of, parentheses, of the sum from k equals 1 to n of f of a plus b minus a over n times k times b minus a over n. Right?
Oh, so we can just use that.
Yeah,
So we don't.
that was a
think
point
of-
to come up with the
okay.
generic formula. I
So-
wanted to do 2 concrete examples to motivate the generic formula, so hopefully when you see this, you see, oh, height of the right point times the base gives me a rectangle, add up all the rectangles, there you go.
So we don't necessarily ever need to go and develop the equation, right?
Well, you better know how to fill this out, man. So let me just write one more step and we'll stop from there, and I think you can do the algebra from there.
Okay.
So this is the same as limit as n approaches infinity of the sum from k equal 1 to n of f of, our a is 1, right?
Mm-hmm.
So f of 1 plus k times,
5 over n.
so we'll just do
Times
5k
5.
over n. Times 5 over n. And I think you can take it from there, right?
I think that, yeah. Would you distribute and then pull them apart? Or would you pull them
Sorry.
apart first?
I should also have this parenthesis.
Oh, I see.
Yeah. There we go.
Okay.
Okay. So, quick note on difference between velocity and displacement. We've already talked about this, distance and displacement and velocity versus speed. Let's quickly remind you of the difference between these two.
Okay.
If I'm walking this way 3 meters per second, and we call that way positive, I have my velocity is positive 3 meters per second. If I'm walking this way, now my velocity is negative 3 meters per second. You with me? But if I'm walking this way, what's my speed?
3.
Meters per second. And if I'm walking this way, what's my speed?
Same thing.
3. So, displacement is equal to velocity times time.
Yeah.
I'm not going to write all this out. I can just say it. Displacement is velocity times time. Distance is speed times time. So if I have a positive 3 velocity for 1 second, and then a negative 3 velocity for 1 second, my displacement is 0. I'm back where I started. My end position and my start position are the same thing. My displacement, 0. My distance was 6.
Mm-hmm.
Okay. I see.
So displacement is just a difference between start and end. And then distance is dependent on the actual path you took.
Gotcha.
So it's possible to have a really big distance with no displacement. That just means you end where you started.
Yeah, like going in a circle.
Okay, so that's the technical difference between displacement and distance. A lot of the times they're the same thing, but there can be weird situations where they're not. The majority of the time, it's the same thing.
Okay.
Because typically, go back where we start. And most of the problems we talk about is just straight line motion. Okay. Important note now, the average height. Average height in the formula for getting the average height of a function on some interval. So, we've got the sum function between A and B. And it's doing whatever it's doing, who knows. There's our function. Now, let's say I want to find the average height of this function, and I know the area. Let's say somehow I'm able to figure out what the area of this thing is. So I know the area is A. And this is some function f of t. How would I get the average height of the function?
Put in a lot of...
Divide it by the base.
Take the area and divide it by the base. And that gives you your average height. What do we want to say? Y average? Something like that. Your average height. Your average height is the height of the rectangle that would give you the exact same area.
As the function.
As the function gives you.
Okay.
So, I know that y times my average height, I know that my average height times my base should have the exact same area as the area of the weird area. And so my average height is just the area divided by the base. Pretty intuitive?
Yeah.
Okay. So they're going to give you problems where they say, let's just do one with actual numbers to give you a sense of what your homework problem is going to be like over and over again. Where you actually divide it up into not n intervals, which you now know how to do, but divide it up into just like 8 intervals and manually do the calculations.
Okay.
So, give you a sense of things that will probably be on your homework problem. Estimate the average value of f of x equal to sine of x. Estimate it, so we're going to use rectangles to approximate it, on 0 to pi. 0 to pi. Now, let's remind ourselves what the sine function looks like. Sine function at 0 is what's sine of 0?
0.
Sine of 0, 0. What's sine at pi? Halves.
1.
1. And then back at pi it's
0.
0. So it's going to curve up and then come back down.
Okay.
We're trying to approximate the average height of that thing. Right?
Wouldn't that just be pi halves? Or 1?
No, the average height.
Gotcha.
Okay. So we're trying to approximate the average height. How are we going to do this? We're going to approximate the area
Okay.
using rectangles.
Mm-hmm.
And then we're going to say that the average height is equal to whatever our area is divided by the length of our base, which is pi.
Okay.
So it all comes down to approximating this area.
Does it want us to divide it into specific rectangles, or do we get to just use this?
You can divide it into rectangles, unless it says something specific. You can almost do it however you want. I mean, there's no wrong way to do it. So for this specific one, he decides to divide it up into 8 rectangles. Okay, so we talked about using the right-hand point, we talked about using the left-hand point. We talked about using the midpoint. There's two more common rectangles that we use. We use the upper rectangle and the lower rectangle. The upper rectangle just means use the highest possible rectangle you can. Pick the highest point and use that as your height. The lower rectangle means use the lowest point. So in this example, we're going to use the upper rectangle.
That makes sense.
Just find what the alpha does. So we're going to divide this into 8 intervals.
Okay.
Okay? So I'm going to divide that. Those are going to be my 8 rectangles. So we're looking at, I'm going to use the highest point. The highest point reached on this interval is right here. So that's going to give me this rectangle. The highest point on this interval is right here. The highest point on this interval is right here. The highest point on this interval is right here. Now notice over here it's going to be the left-hand point that gives me the highest.
Yeah.
Rather than the right.
Why would you want to do that?
It's when you come at calculus rigorously, so in like a real analysis class, you really only use these upper and lower rectangles, and you really only ever sum those up, and we call them upper and lower Darby sums, and then you calculate the integral is sandwiched in between those. So you really take the limit of the lower Darby sum, the limit of the upper Darby sum, sandwich the actual value of the area in between them, and that's how you calculate the area.
Okay.
Because you can evaluate the upper and lower Darby sums. So,
I see.
but doesn't matter. Okay, anyways, so now we need to manually calculate each of these rectangles. So here's the annoying part. So our area approximation is going to be equal to, what's the base here?
Pi 8.
Pi 8 times the height.
Sine of pi 8.
Perfect. Plus, what's the base?
I
Pi 8.
Why are we blessing pi 8?
I gotta calculate this rectangle now.
Oh, you're doing it for all of them.
Times the height.
2 pi 8.
2 pi 8 to pi 4s, right?
Yeah.
Plus, and you get it, we need to calculate each of these. Plus, all the way to the very last one.
Okay.
7 pi 8.
Well, pi 8 is going to be my base. And then my height, we calculated that with the left-hand point now, not the right. So that one is 7 pi 8. Sine of 7 pi 8.
Oh, I see.
Right?
Yeah.
Now you use your calculator to get, first off, when you're actually calculating these, make sure you factor out your base. Don't actually multiply by n each time. So you just need to sum up your heights.
Okay.
Yeah. So this is roughly pi 8 times the sum from k equals 1. No, can't do it like that because we don't always use the same point. Sorry. So sine of pi 8 plus sine of pi 4s plus sine of, let's see, pi 8, this was
3
pi
pi
8,
eights.
this was pi 4s, this was 3 pi 8s,
Yeah.
3 pi 8s for that rectangle, plus, notice that both this rectangle and this rectangle use sine of pi halves, so we'll have 2 of those, 2 sine of pi halves. So that takes care of those rectangles plus this rectangle. What do we use for its height?
5 pi 8.
Sine of 5 pi 8, not quite 3/4 yet. This one we use 3/4. 3 pi 4s. And then for our last rectangle, we use plus sine of 7 pi 8. Just writing one out completely, very explicitly, so that you know exactly how to do it. Notice that we had a weird transition point in this. Because we were using all the right-hand points, and then suddenly using the left-hand points. So plug all those numbers into your calculator, see what you get.
And that's
Multiply it out, and that will give you your area. So the area comes out to roughly 2.364. But you can figure out how to get there, right? No point watching me plug into the calculator to say, yep, that's what we get. Okay, so that's our area. So our average height, we need to divide the area by pi.
okay.
So remember, we were after the average height.
Yep.
So So our average height, y average, is roughly, when you take that divided by pi, you get roughly, better be less than 1 and more than half, 0.753. Which is believable. Okay, so there's an example of a homework problem you might have.
And that's the section 1, right?
That's 5.1.
Okay.
So 5.2 we already covered most of. That was all the sigma notation stuff.
Mm-hmm.
So now we got to go back and talk about when we're actually dividing up this interval, calculate an area. Well, okay, take a step back for a second. Now we're just going to talk about a partition, and we'll see how it comes back into the picture. Partition. What's a partition? So if I've got some interval on the x-axis, here's A, here's B. What is a partition of AB? A partition of AB is a set of points x0, x1, x2, xn. It's some set of points where x of 0 is equal to A, is less than x of 1, is less than x of 2, is less than is less than x of n is equal to B. Okay, what does that mean? It means if I create a partition of AB, I call into n points, give me some actual number n. 7. 6, okay. So we're going to create a partition on AB where n is 6. With me?
Okay. Yeah.
So here's x of 0. X of 0 always has to be at A, your start point, what you're partitioning. And x of 6 has to be at B because we're going to divide this up into 6 pieces.
Okay.
I see.
Now any other partition, it doesn't matter where you put x1, x of 2, x of 3, x of 4, x of 5 for it to be a valid partition. They just have to be in ascending order.
Okay.
So I can't have, here's a bad example. I can't have x1 there and then x2 here. Nope, bad. If x1's there, x2 has to be to the right of it. So then I can have x2 there, x3, x4, x5. That's all I'm saying.
Okay.
You with me so far? So this is a partition on AB. We would call P a partition on AB. P is a set of these points.
Okay.
So P equal to the set x0, x1, x of 6 is a partition on AB with the pitch right there. That's what we mean by a partition. Pretty straightforward?
Mm-hmm.
Okay. So notice now, even though we have 7 points here, 1, 2, 3, 4, 5, 6, 7, we divided this interval into 6 pieces. We divided it into this piece, 1, 2, 3, 4, 5, 6. So 7 points gives you 6 segments.
Okay.
Right?
Yeah.
2 points gives you 1 segment. 3 points gives you 2 segments. 4 points gives you 3 segments, etc. So we start with x0, we go to x of n. This partitions AB into n segments, n pieces, n subintervals, whatever you want to call it.
Okay.
With me so far?
Yeah.
Okay. Let's see. Yep, that's partition. General notation. So redrawing my picture from up there. Here's AB. Guess we don't need to do that. Here's AB, here's x0, here's x of n. We'll say here's x of 1, here's x of 2, Here's x of k minus 1, here's x of k, So we have more points, right?
Mm-hmm.
We call this distance right here, just notation, delta x sub 1. The change in x on our first little interval.
Okay.
This is delta x sub 2, delta x sub 3. The change here we would call delta x sub k. Just notation.
Okay.
Okay? A random point in any of these intervals we signify with c sub k. So c sub 1 would be a random point in this interval.
Okay.
That we're just picking out, right? Okay.
C sub k would be a random point in that interval. Could be the endpoint, but any point in between. Just notation.
So why are you introducing this notation?
Because when we give you the exact definition of an integral, we're going to need some of this notation.
Okay.
So notice that creating a partition, we created a partition of even pieces, right?
Yeah.
We divide this into n even pieces. Well, it turns out in the precise definition of an integral, you don't have to divide them into even pieces. You can partition it up however you want, as long as your partition follows some rules. So we were being a bit too specific, or too restricting in requiring it to be an even partition here.
Mm-hmm.
And notice that we also always use right-hand point. We didn't have to use that. We could have used any c sub k in each of those intervals. F of c sub k to get the height.
I see where
So we're setting up notation to help us give a precise definition of an integral.
Okay.
we prove partitions, right, in discrete?
We use partitions. You use partitions, very common mathematical structure. We use them in discrete, we use them in topology.
That's right.
Maybe that wasn't topology, maybe that was real analysis.
I know we use them in
Let's
discrete.
get a little blurry in my mind. Yeah, we use them in discrete, but in discrete, a partition was something slightly different. It wasn't just this.
Yeah, it is different.
So that was one of those places where you have the same word meaning two different things depending
Why
on
are they
the
different?
context. Because that was partition. I mean, they're technically doing the same thing. Look, when you partition up in discrete math, you're just taking points and separating them into separate sets. So that everywhere goes into one set, and no 2 points go to
The same set.
two different sets,
Oh yeah.
right? So it's just like if we partition the student body up into a bunch of classrooms. That's partition,
Yeah.
where it's those sets. Here, it would be kind of verbose to say, if we use the same discrete math notion of a partition, we need to assign all the points here to a partition, all the points here to a partition, all the points here to a partition.
I see. Okay.
And the problem you have there is we want x1 to be in two partitions.
And two, yeah.
Yes. Because this partition is including x sub 0 to x sub 1. And then this partition is including x sub 1 to x sub 2. There's your slight distinction.
That makes
So
sense.
now it's quite the same.
Okay.
Okay, so in each subinterval, we select a point, call it c sub k. Then each subinterval will stand for a vertical rectangle that reaches. Okay, so should have drawn my function on this picture as we go. Here's my x-axis. We got some random partition here. Let me just redraw the picture altogether. Sorry, should have drawn a bit bigger and been ready for this. So setting up for the notion of an integral once again in a more generic way. So we got our function here. Here's our a now. We're going to be doing the area from a to b, right? Of some function. Doesn't matter what it looks like. Here's a. Here's b. So first thing we do is we create some partition on this thing. We divide it up into n pieces. So this is also your point x of 0. This is also your point x of n.
Okay.
And then we have maybe there's x of 1, there's x of 2, blah, 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 blah. Here's x of k minus 1, and here's x of k. With me?
Mm-hmm.
C sub k is some point in between. So C sub k is right there. Some random point in between.
So it doesn't
Not
matter
necessarily
where.
the midpoint.
Okay.
Could have been that point, that point, that point, some point in between. Okay. So a rectangle then that we could construct here, where we use this point to get our height, would look like this. Roughly, right?
Yeah.
Where this height right here is f of c sub k,
Mm-hmm.
right? So the area then of this rectangle is what?
F of c sub k times c sub k, right?
No, c sub k is just that x coordinate.
Oh,
Base
it's
times height.
delta of c sub k, right?
So it's the height is f of c sub k
Mm-hmm.
times the base.
Why is it x sub k?
Remember I told you that that was our notation for the change in x on some interval.
Yeah, but don't you have it written as c sub k?
No, c sub k is a random point there. Delta x sub k is the change in length on our kth interval.
Oh, I see it.
Good?
Yeah.
So notice when we were doing it over here, we were always making our changes in x the same. So for our special case where we were always keeping our changes in x the same, it would look more like this. f of c sub k times v minus a over n. Because we made every interval change by this much.
And that's the midpoint formula, right?
No, this is still just a random point, so I'm midpoint. Midpoint means the exact middle.
Oh, and you're picking any point in between.
Any random point in between.
I see.
Okay, so this is a random height, but when we were doing it, we were always using this for our distance. We chose partitions that divided it up into equal lengths.
Okay,
If you don't do that, then here's your formula.
I see.
If you divide it into even lengths, okay, here's your formula. You with me?
Mm-hmm.
We don't have to use even lengths. It's just convenient to use even lengths because the math comes out nice. But we didn't have to with our definition of an integral. That's why I told you, when I go to calculate an actual integral, I use that formula I showed you. But it's a very special case of the generic formula. So we're working our way up to the generic formula.
Okay.
So now, here is the area of any random little rectangle.
Yeah.
With me?
Mm-hmm.
Okay. So, he wants to call it the sum. Then the sum, the approximation for the area, the sum is going to be the sum from k equals 1 to n of f of c sub k times delta x sub k. That's summing up all our, I'm going to call it area. Our area is approximated by that sum. Maybe call it the sum since the area is only when we take the limit.
And that's what the generic form?
Almost.
So we're just
We
getting closer and
haven't
closer.
taken the limit of this yet.
Oh, I see.
We need to put a limit on this somehow. And how we take that limit, there's a little bit of technicality with it. But this is a generic way. This is a more generic way of getting an approximation. Right?
Mm-hmm.
So we didn't require specific using the same interval every time. We didn't require using the right-hand point. We said use any point on the intervals and use interval lengths of whatever you want. Here's an approximation. And just to be a little bit verbose, let's make sure that we see what this is saying. This is saying f of c sub 1 times delta x sub 1 plus f of c sub 2 times delta x sub 2, meaning that point and that point are very different points, and that distance and that distance are very different distances, etc. So there's no necessarily repeating terms. You can't factor anything out.
But it gives us
It's going to give us
the
an
whole
approximation.
distance.
It will give us an approximation.
Okay.
Not necessarily a good one, but an approximation.
What gives us the actual?
When we take the limit. We need to take the limit to get the actual. we need to use infinite rectangles.
Oh, well, how did you take the limit of that?
We'll get there. That will be 5.3.
Gotcha.
Setting up a generic approximation, here it is.
Okay.
Any wild random approximation you choose to approximate the area here
Can fit into that equation.
fits into this.
Okay.
Okay. And so this is called, just verbiage, this is called the Riemann sum for f on the interval AB. You probably don't care too much about that terminology. Okay. So 5.3, strongly recommend that you go read that section now, which is now going to take this, take the special limit on it,
Mm-hmm.
and give you the actual integral.
Okay.
And maybe I'll just give you the picture right now and give you what it all comes down to.
Okay.
Okay, so how do we get an actual integral? We need a special type of partition. Partitions.
Special type.
Yes, so this is a partition with, let me give you an example of a terrible partition that we could use. Okay? A terrible sequence of partitions, sorry. So imagine I want to approximate the area under a curve. It's not enough just to break this up into infinite pieces, is what I'm going to show you. It's not enough just to use infinite rectangles. That doesn't guarantee you that you get the area. And I'll give you a very intuitive example of why that doesn't work.
Wait, you have to pick a number to do that though?
I don't know what you mean by that, but
Okay, it's just,
I'll show you why just using infinite rectangles doesn't necessarily work.
okay.
Okay? So, let's say that I start out with, because you know how we did it before, we take the limit as n goes to infinity, so we start out with splitting our interval up into 10 pieces, then 11, then 12, then 13, then 14, then 15. So we keep making our partition have more and more and more and more and more points. We keep using a bigger and bigger partition in terms of how many points are in there.
So our partitions.
So our partition, for how we were calculating integrals before, ended up having infinite points in there, right?
Mm-hmm.
As n went to infinity, each partition had n points in there.
Yeah.
You with me?
Yeah.
What I'm going to show you is that just that requirement isn't enough to get the area. Even if your partition has infinitely many points, that doesn't mean you're getting a better approximation of the area, or a perfect approximation of the area. They don't all have to be the same size.
They don't.
No.
Yeah, that's what.
So we're going to make sense of what the one requirement is that they have to have. Okay?
Okay.
So let's start out with some generic function. And my partition, we'll just do 0 to 1 to keep the math really simple. And the first partition I'll use is p equal to 0, 1/2, 1. So that's using this 0, 1/2, 1. Here's our rectangles. Doesn't matter what point we use in between there. So here's my c sub 1, and here's my c sub 1, here's my c sub 2. Doesn't matter which points we use in there, but there's our two rectangles, right?
Okay.
So for my next partition, let's say I look at this partition. P equal to 0, 1/2. Sorry, 0, 1/3, 1/2.
Okay.
So now what does that do? That takes this picture, and now we add a point at 1/3. So here's 1/2, 1/3 like right there, right?
That's
And so now we have these rectangles. Right?
Okay.
And now I can do P equal to, for my next partition, I'll call this partition piece of 0, piece of 1, piece of 2. Piece of 2, actually let's call this piece of 2, well, doesn't matter what we really call it. Okay, good enough. Let's say for our next partition now we do 0, 1/4, 1/3, 1/2, 1.
Okay.
So now that adds another point right here.
yeah.
Now say I put 1/5 in there. That adds a point here. And then 1/6, 1/7, 1/8, 1/9, 1/10, 1/11. And let's say I add all the numbers 1 over n into the sink. That adds infinitely many points, right?
Yeah.
And it creates infinitely many rectangles, right? None of them changes the fact that our approximation with this first rectangle right here is garbage.
But you
Notice
can
that
fix
this
that.
rectangle never gets better. So even if I have a partition where I divide it up into infinitely many pieces. Sure, we're approximating the area over here really good, but we never got a better approximation of this area.
So your rule is that you have to do it infinitely the whole
Keep thinking about it, because I think you might get there.
okay.
So our problem is that what's the width of this rectangle right here?
1/2.
1/2, and that never changed. We never made that any smaller.
Yeah.
What do we need the width of that rectangle to approach?
Infinity.
0.
Zero.
0, sorry.
0. So we need all our intervals to approach 0.
Yep, that makes sense.
Okay, so we call the biggest gap between 2 points in our partition, we call that the gap of our partition, or the norm of the partition. Sometimes it's written like that, sometimes it just has 1, sometimes it has 2. See what our author's notation is?
The norm.
The norm. It means the biggest interval in our partition. So the norm of this was always 1/2. For all these partitions, our norm was 1/2.
And so you're
Because
saying
that was the biggest gap between 2 points. So we need our norm of our partition to go to 0.
so it's saying look at your norm of your partition, make it go to 0, and then keep going. What, to the next one?
You take the limit of your sequence of partitions. Notice that we have a sequence of partitions here
Yeah.
that we keep adding points to. If in the limit, your sequence of partitions, if the biggest gap between 2 points goes to 0, you're good.
I see.
Does that make sense? So I'm going to give you the definition now. We take the limit.
Of an integral?
Yes.
Okay.
We take the limit. I mean, you have this in your book. We take the limit as the gap, or the norm of the partition, goes to 0 of the sum from k equals 1 to n of f of c sub k times delta x sub k. And let me rewrite the one that we had up here so that you can see how they're connected. And see how it's just a special case. Good? Okay, so let's read both these and see how they're saying the same thing. So this is saying take the limit of your sequence of partitions as their biggest gap goes to 0
Okay.
of the sum of the rectangles, height times base. And as long as these distances are going to 0, we're good.
That's what it's saying.
Yeah.
Gotcha.
This length, the norm, is going to be one of these.
Okay.
It's a distance between 2 points, right?
Mm-hmm.
So the norm of this thing was 1/2. You with me so far? Okay, so notice, now let's look at this thing. We want the limit as n goes to infinity. Well, notice that our gap, our norm, is always b minus a over n. When we do evenly divided.
Yeah, because they're all the same.
Because they're all the same. So if they're all the same, then they're all b minus a over n, right?
Mm-hmm.
So notice, as n goes to infinity, b minus a over n goes to
0.
0. So we do have our norm approaching 0.
Okay.
Okay, notice that.
Mm-hmm.
Times, or the limit of the sum of the height, we chose the right-hand point. You can use any point in there. We're always using the right-hand point. Times the base.
Yeah.
You see how this is just a very special case of this? And you'll notice that this isn't like a generic formula that you can work with that well. You need to start picking things to get to something you can start doing math on. You can't take something this generic and start doing math. You need to pick which points you're going to plug in and what your distances are going to be. So here we've chosen a very specific sequence of partitions. Here it's still up in the air. So notice there's tons of ways that we could have gone from here. We could mess with this. This is just one. This is a very special case of this, where we're evenly dividing the partition.
Do we go over all the cases, or is it infinite?
There's infinite cases, but yeah, there's no point We just need to find one case that satisfies the definition, and we're good. And we can work with it.
Yeah.
It's like me saying, look, there's an infinite number of ways that we could write this number. Right?
There is.
Another way I could write that, sure, I could write this as 81/32.
Okay.
I can also write this as 100 minus 19 over 40
I see.
minus 8. There's an infinite number of ways I can write it. One of them is the most useful way to write it for our certain situation. There's an infinite number of ways that we could interpret this. This is pretty much like the most useful way for most of our problems.
Okay. I'm a little confused, and that's that we can find the area of that, right?
Of
Like,
this,
Yeah, we know how to.
not using this method.
So it's the
We need to
method.
use this type of method. We need to use something like this. Yeah, if I use this,
Then we could.
then I could easily.
I
The
see.
point was this method is not going to give us an area. Because this approximation is garbage and we're never fixing it.
But you can find the area of any line, right?
No. You can't integrate any function. And we will not be dealing with functions that aren't integrable. But integrating compared to differentiating is much, much harder. And
Okay.
there can be relatively simple looking functions that you cannot integrate.
You want to give us an example?
No.
Okay.
Not right now. Because there's no point yet.
Will we come across them?
I don't know if we will in this class actually. Might be more of a chapter 2 topic. But you can always approximate it. You can always use rectangles to approximate it.
Mm-hmm.
You just might not be able to get a perfect calculation. Some of them you can't get a perfect calculation on.
So you can, to some extent.
You can approximate it. You can
Okay.
approximate anything, sure.
Okay, I see.
But getting a perfect calculation is different than an approximation. And some functions you can't perfectly integrate. You can always approximate, sure. So if you understand what an integral is, you can always go write a quick calculator to come up with an approximation of whatever function you're talking about to the extent that you care about it. Yeah. Because you might not be able to integrate it. It might be impossible to integrate it. Not that you're not clever enough. It might be provably impossible. It doesn't have an integral. Or at least one that we can express algebraically the way we're used to. Anyways, that's it for today.